This module is on rotational motion. So instead of moving along the line, we will spin the objects like this. And we need to describe their motion in terms of their position, velocity, and acceleration, which will be kinematics and then dynamics. How will we do that? Instead of working with x and y coordinate system, we will introduce polar coordinates. And actually, we already did it. And please watch the derivation of velocity and acceleration in polar coordinates from the previous module. But in this video, I will summarize all formulas that we will need to solve problems on rotational motion. So as this object, any object moves, we will describe its motion in terms of r and angle theta. And we introduced new unit vectors. Unit vector IR that is always along r, and unit vector I theta that is perpendicular to IR. Now, consider this situation. I'm spinning this eraser, and this eraser is attached to the spring. This is this eraser, and let's think about string. Better, let's think about it as a rod. So radius is fixed. I'm looking at it from above. This is top view, and I'm spinning it. So this ball is going around the circle. Now, if I'm spinning it, this angle is changing. And how to describe change of angle? We introduce angular velocity, omega, which is rate of change of angle, d theta dt. Now, what if I'm spinning it not with constant omega, but omega is changing with time? Then d omega dt is non-zero, and we call it alpha, which is angular acceleration. And we also introduce period 2 pi over omega, time that this eraser needs to complete one revolution. All right, so let's consider again this specific case. What is this specific case? R is constant. R is constant. And also, I want to spin it with omega, rate of change of angle. That does not depend on time. So R is constant, omega is constant. Some of you already considered this case in your high school classes, but I will write these formulas for this specific case. R constant, omega constant. What will be the velocity of this ball and what will be the acceleration? So from our lectures, from the textbook, we know that for this particular case, the velocity of the ball will have tangential component like this. So this will be velocity of the ball. I will call it v theta. It's along I theta. And v theta, this tangential component of linear velocity, is equal to r. In my case, r is called capital R times omega. V theta is r omega. But omega is omega is 2 pi over t over period. So I will write it as r. And then omega is 2 pi over t, or I will write it in a better way as 2 pi r circumference divided by period. And this is my v theta for this specific case. Now, I also know the acceleration for this case. The acceleration for this case will be directed towards the center. This will be my acceleration, A, towards the center. And I will write the projection AR. Since my IR is out of the circle, that's what I decided to go. This is my choice of the coordinate system, and I will always stay with it. My IR is out of the circle. Then projection of this acceleration is negative, since acceleration is towards the center. And what is the magnitude of this acceleration? It is r, radius of this circle, omega squared. And in some books, it is called centripetal acceleration. Towards the center, magnitude r omega squared. Now, if I express omega in terms of velocity, linear velocity, and radius, omega from this first formula, what is it? It is v theta over r. I bring it here. It will be minus r. Again, minus because projection is negative. Minus r omega squared is v theta squared over r squared. R squared, what do we get? It is equal to minus v theta squared over r. And you probably recognize this formula. So what was the magnitude of the centripetal acceleration? Just the magnitude. It was v squared over r. Sounds familiar to you, right? And velocity is 2 pi r over t. So we know how to describe this specific situation. We know how to find velocity and acceleration. We know these formulas. However, imagine this. Instead of spinning it with constant omega, I can accelerate like this. Then what will I do? Omega is not constant anymore. Will these formulas be correct formulas? No. So we need some general case. We need velocity and acceleration in polar coordinates that describes all these cases. So for example, instead of having r constant, I can have r changing. Imagine that the length, let's see that. So imagine that this is merry-go-round and I'm standing here and this merry-go-round rotates and I start walking towards the center, which means that r is changing. What will be my velocity and acceleration? I need to figure it out. So in the previous unit, we derived the general formulas on velocity and acceleration in polar coordinates, and I will write them here. So in general case, I have radial component of velocity, v sub r, as dr dt. And my tangential component of linear velocity is r omega. My radial component of acceleration is described by quite long formula, but I will write it here, and I hope that you will have these formulas in front of you. So when we start solving problems, these formulas will be extremely helpful. d2r by dt squared minus, I put this bracket for no reason. Let me erase it real quick. No bracket here. No. d2r by dt squared minus r omega squared. This is a sub r. And a theta, tangential component of acceleration, will be 2 dr dt omega plus r alpha. So in our new coordinate system with unit vectors ir and I theta, I can write the velocity as vr ir plus v theta I theta, and I can write the acceleration as ar ir plus a theta I theta, and both components of velocity and both components of acceleration are written here. And one more step. We will need to find forces acting on this ball, or we will need to find omega if we know forces, something like this. So we need Newton's second law. F net force as a vector is equal to ma, acceleration a as a vector. And I will write it in terms of components. Net component in radial direction of the force is equal to mar, and this is equal to m, and then d2r by dt squared minus r omega squared, our ar component of acceleration, and f theta, net force in tangential direction, will be ma theta, and it will be m, and then 2 dr dt omega plus r alpha. And now I believe we have all formulas that we need to be successful to solve problems on rotational motion. Next video, problem 1.